Hello, this video introduces moments in mechanics. We all experienced this when we were children and we went on the seesaw with our parents, and the greater weight of the parent pulled their end down compared to the smaller weight of the child. And then we worked out that if the parent moved closer to the pivot point of the seesaw, you could balance it out. So what we learned in effect was our fundamental principle that what's really happening is it was the weight times the distance that made the difference, wasn't it? And we could, as long as we balance those two out, we're okay. Now that weight times distance is called a moment, and the point in the middle of our seesaw we're going to call a pivot point, because we're going to work out the moments about that point. Okay, let's put some maths on this. So a moment is a force times a distance, and therefore that distance must be from some sort of point. So here's our pivot point here. I've got a lever arm, a distance, and then I've got a force, yeah? And that's creating a tendency to rotate, in this case in the clockwise direction, isn't it? Because that's pulling us down. Here I've got this point. Again, I've got a force at this distance, and that again is causing us to rotate in a clockwise direction. And in the final case here, I've got a force at this times a distance, and that's creating a rotation in the anti-clockwise. Now each of them's creating a rotation. If they had the same force and the same distance, they're creating the same moment. Doesn't matter the fact this one's going straight down and that one's going over to the right in the clockwise direction, that's going to the right in the anti-clockwise direction. The only difference here is the sign of it, whether it's clockwise or anti-clockwise. They are the same moment. However, in all these cases that I've just drawn, we were interested, I drew them all with a right angle, yeah, between the lever arm and the force. Now that's not the only situation we may find. We could have one like this example here, where there's an angle between the lever arm and the force. So we need to be able to take account for that. And there's two ways of thinking about this. First one, I've drawn this diagram on the left hand side where I've still got the force pointing down. What I've done is draw this perpendicular line across here with a right angle, because what I can see is that this force is effectively acting at a reduced lever arm, and that reduced lever arm is going to be d sine theta. So one way of thinking about it is that the moment is the full force multiplied by a reduced lever arm d sine theta. The other way of thinking about it is what's happening to our force. Well, actually the force, if we split it into components, there's a component that's just acting towards the centre, that's not creating a rotation, and then we've got a component at right angles to the lever arm. There's our lever arm, so we've taken it at right angles, and that angle, that reduced component, yeah, it's a component of force, is f sine theta, isn't it? So that's another way of thinking it, that we've got the component force, which is smaller, f sine theta, multiplied by the full lever arm. Either way, we end up with this formula that the moment is the force times the distance times the sine of the angle between them. So that's our first key point. That's what a moment is and how we can calculate it. Second thing to think about is that we're really dealing with these in rigid bodies. In the past, all our work was done where we assumed that there was a single particle and all the forces operated on that particle, so there was no rotation going on. But what's happening here is we're going to get some rotation. If I have this beam, it's got a centre of mass there in the middle of the beam, and I attach a force to the one end of the beam, well, it's going to try and rotate the beam round, isn't it? It's going to try and rotate it around its centre of mass. The centre of mass doesn't want to move. Yeah, that's what it's going to try and do. It will actually try and pull it down a bit, but the key bit is it's going to try and rotate it. Similarly, if I had a block of wood or block of concrete, there's a centre of mass, I attach a force to one corner of it, it's going to try and rotate it round. Or if I had a frame, like a bridge or something, a frame, a truss and a bridge, centre of mass would be in the middle of this triangle, would be 1/3, 1/3, 1/3. Around the triangle. That force is going to try and rotate the frame around the truss, isn't it? So all times the second part of our idea is we've got a rigid body that if we've got a force and it's not at the center of mass, it's going to try and rotate that body around. Okay, let's start thinking about resultant moments. We've done a lot of work in our F equals ma, look at resultant forces. Well, does the same happen in moments? Let's have a think about our seesaw, see what's going on, and see if we can get our seesaw, work out what the moment is. Well, what's going on here? Let's start thinking. I'm going to think about this, the force of the child. So I've got a small child here on this right hand end. It's 1 meter away from the pivot point on our seesaw, so that's creating a moment, a clockwise moment, isn't it? And I'm taking my force times my distance, and I create my moment for that body B, for the small child or baby. 10 gram, 10 g, rather, for 10 kilogram. 10 g is the force, and 1 meter. So what am I looking at there? I've got a moment of 10 g newton meters. So that was dealing with force A. Now we've got body B, sorry, force B. We've got body A here, which has got a force where it's got a weight of 50 kilograms. So that's got a force of 50 g, and that's at 0.5. And it's in the it's trying to make the beam rotate in the opposite direction. It's trying to do it in the anti-clockwise direction, isn't it? So I could work out what this moment is. Well, it's going to be that force times that distance, and that's in the anti-clockwise direction. Yeah. So the moment that the body A is creating is 50 g times 0.5 as the distance. So it's 25 g, and that's in newton meters. Yeah. So that one's going anti-clockwise. So that's greater, isn't it? The moment from the adult is greater than the moment from the child. So we're going to have a resultant moment. It's going to start to turn anti-clockwise, isn't it? If I therefore want to work out what my resultant moment about the pivot point is going to be, well, it's the anti-clockwise moment of the adult less the clockwise moment of the child. So that's 15 g in newton meters. There we go. So yes, we can create resultant moments, and these resultant moments tell us what the direction of motion would be if we're in motion. Okay. Next step I want to think about is how we can use moments to find forces. I've extended our problem here, and rather than having a single pivot, I've got a beam supported at either end at P and Q. So that's the same as a bridge, isn't it? If I put a weight in the middle of a bridge, and what I'd like to know is what forces are at either end. Now at present, from the work we've done, all we know is that there are reaction forces at P and Q must equal our weight force here of the body we're supporting. What we like to do now is to find out what the individual reactions are, and we can do that by taking moments. So I'm going to start by taking moments about one end, and I'm going to start by taking my moment about P. Now the important thing about that is I've got two other forces to deal with, the RQ force and the 50, because they're creating moments, aren't they? But actually, by taking moments about P, I don't need to bother at this point about the reaction force at P, because it's at no distance away, so it can have create no moment, yeah, because the distance the lever arm is 0. So let's work out what is my moment. I'm going to take moments about P, and I'm going to take them clockwise. Now I would show this, if I'm doing my work, by drawing a symbol here. I've put the letter P because that's the point I'm taking moments around, and then I've put a circular arrow with a direction on it because that's showing that I'm taking that in an anti-clockwise, in a clockwise direction. So what's the moment about P then? Well, I've got this force here, the 10 g times that distance. So for my mass that I'm holding up, I've got 50 g times 0.5. So that's a clockwise moment, isn't it? But that's being held up by an anti-clockwise moment from the point Q. Yeah, that's what's holding it up. So what's the moment that's creating? Well, it's got the reaction force at Q, times 2 meters, that full distance from the pivot point. Yeah, so there we are. Now that gives us a resultant moment, doesn't it? Now if this is an equilibrium, if this body, this beam, is not moving, the resultant moment must be 0. Yeah, so MP would be 0. Yeah, so we could think of it in two ways. Either we can write it as the resultant force is 0, or you could write it as a balance, that the moment of the weight force, the thing that's being held up, must balance with the reaction moment from the end support. And we can just rearrange that equation now, can't we? And we find that the reaction force at Q is going to be 12.5 G. That's in newtons, isn't it? And then we can do exactly the same thing to find Q, the force at Q, sorry, at P. So if I now take moments about Q, there we go, I get no moment from Q because it's got no lever arm. I've got these two forces to deal with now. I've got this force coming down, creating a anti-clockwise moment, and I've got this force here going up, which is creating a clockwise moment, isn't it? So again, I could create my resultant moment. If you think I'm too far, here we go, which is the weight and the distance it is from Q, and then I can look at the reaction force at P and the distance from Q, that's 2 meters again. Again, if it's 0, I can just go in the equation for that, or balance the two moments, and that allows me to find that the reaction force at P is going to be 37.5 G, and that's in newtons. Of course, it's worth bearing in mind that we should be able to check that there's no overall force. Yeah, so the two reaction forces should balance with the weight of what's being supported. So if we just got those two values, we just calculated 12.5 and 37.5, we got 50 G. So if we've done our calculations correct, it should be 50 G because it needs to balance the weight that's supporting. So there we are. Quick summary then. A moment is a force times distance. It's got to be taken about a point, and if the two, if the force and the lever arm are not at right angles, then we need to adjust by adding the sine theta into the calculation. If a body's in equilibrium, then the clockwise moments and the anti-clockwise moments have got to balance, and that's got to happen at all points. So we can take moments at any point and they'll be in balance. And finally, if the moments are not in balance on a rigid body, the moment is going to try and make the body rotate about its centre of mass. So there we are. First start.